Alright, so today's first topic here is something, it doesn't really have a proper title in the book. It's marked off as a different section, but I'm gonna write it here as injectivity of a restriction map. Because if you recall, we kind of so if you recall the map from BL of G of B to BH of W was stated to be injective. It wasn't actually needed, so we didn't prove it, but there's this kind of like hand-wavy term at 1.2 regarding like algebraic geometry, but it wasn't essential to proof, so we didn't actually go into it last time. So this time here, we're going to go into it here. So we're going to let A be our field to the n without ignoring the vector space structure. They call this here the affine n space. I know traditionally affine means that it looks very similar to being linear, except you don't have necessarily an element which acts as 0. I'm wondering if that's what they're going for here. So we're going to let, what we're going to write is ft be the polynomial ring in n indeterminates from 1 to n. Now this is all going to be more topology focused, it looks like. If I is an ideal in f of t, just keep in mind this is a polynomial ring. We're going to let v, I think that's supposed to be v of I, be the set of x with components I from 1 to n in A, such that fx is 0, 0 for all of the polynomials in I, in our ideal. We topologize A by declaring the sets of Vi to be closed. So then obviously the empty set is going to be given by every polynomial, I believe, and everything given by the empty ideal are closed. And the closure of intersections and finite unions can be verified. E.g., so we can start out, you can get started on this by seeing that phi of the sum of I alpha ideals over some alpha is the union over those alphas of our v I alpha, and so on. This topology on A is called the Zariski topology. Don't know if I'm saying that name right. I never know if I'm saying any name right. And if f is the reals or the complex numbers, a Zariski closed set is closed, but not conversely. So this set is coarser, I believe, than the standard topology on RNC. Now, if we have a polynomial in our polynomial ring, the function from x to f of x as a to f is called a polynomial function on A. Such a function is going to be continuous in the Zariski topology. I'm just going to write a Zariski. F being given the Zariski topology, or maybe in this context, affine is just referring to the fact that we don't have vector structure on it anymore. Of affine one space. Since f is infinite, which is a very weird way to phrase it, the only polynomial vanishing on f is 0. A subset of A is called irreducible if it cannot be covered by two closed sets without being covered by one of them. Essentially, this is a stronger form of connectedness. Essentially, if you have like a little set here, if you have a closed set and then another closed set, it has to be in, see, like this case, it's inside both of them. So this is going to be irreducible. Where on the other hand, you're not allowed to have something like, if you have like this and then another one covering the rest. It's actually hard to draw, I think. Something like this would be irreducible, where there's like a little bit of it hanging out on either side of the set. Alright, so our first lemma just states that A is irreducible. And the proof: let A be the union of the closed set of an ideal unioned with the closed set of another ideal. with both of these vi being proper. So not all of A, I believe that means. Or both being non-zero. Potentially both. Then I1 and I2 are not 0. Now let f be a polynomial from I1, g be a polynomial from I2, be non-zero. Then fg is not 0, but fg vanishes on A. And this comes with a corollary. So you set non-empty, open sets in A are dense. So every open set in A, I believe, intersects it. The proof: let U be a non-empty open set. And of course we want that U is dense. Yeah, if U is not dense, there exists a non-empty open set V and A, with non-empty open set V and A which does not intersect U. Then A minus U and A minus V, which we see are closed, are proper. And cover A, which we saw from our lemma that that's not going to be happening. So now we're going to let L be semi-simple, H a Cartan subalgebra, and so on. All of our usual setups. Fix a basis of L so that L is identified with the affine n space, where n, of course, is going to be the dimension of our L. And from this, BL with the polynomial functions. In the sense of our previous study here. Relative to this basis, adjoint of X, of course, is an n by n can be represented by an n by n matrix. Whose coordinates are linear and hence polynomial functions on L. Now we're going to let T be an indeterminate and rate, and I guess I'll put that first. Then for an x and L, write px of t be the characteristic, this is going to be the characteristic polynomial of the adjoint of x, and it's going to be cix ti be the characteristic polynomial of adjoint of x. And we see that each ci is a polynomial on x. On L, sorry. We're going to call the row rank of L the smallest integer m for which Cm is not identically 0. And we're going to call x in L row regular if Cm of x is non-zero. Thus, x is row regular if and only if 0 has the smallest possible multiplicity as an eigenvalue of the adjoint of x, thus x is row regular if and only if its semi-simple component is, since they have the same characteristic polynomial. With this giving us the obvious fact that row regular semi-simple elements exist. Now the set off. That's going to be a fancy R. That's the best I can do, I think. Of all row regular all row regular elements of L, and this is going to be open, and being non-empty, it is dense. If x and L is semi-simple, it lies in a maximal toral subalgebra So the conjugacy theorem we saw earlier implies that X is conjugate under G to an element of H. But, however, if H is an H, we know that the dimension of the centralizer in L of H is at least L, being the rank of L. And we also know H possesses elements which we call regular. For which the dimension of the centralizer in L of H is L. Since row regular semi-simple elements exist, they then must coincide with the regular semi-simple elements, with our M from the row regularity being our L from the regularity. So, but no potent element other than 0 centralizes a regular semi-simple element. From this we see that X being row regular implies that X is X of S. Sorry, things are happening. So, thus, our fancy R, which thankfully is still in sight, so I remember how to draw it here. I did no great job though. Is the set of all regular semi-simple elements. So, now let F be a polynomial on L invariant under the inner automorphisms, whose restriction to the Cartan subalgebra we've chosen is 0. Then F vanishes on our fancy R, which we know is dense. So F is 0. Thus we have finally that theta from the G invariant polynomials of L to the Weil invariant polynomial elements of H is injective, as we want. So that's, I guess, going to be the first half of this video. Now we're changing chapters to next one, as you do, which is on formulas by Vile Constant. I'm bad with last names. And Steinberg. Everyone in math has a weird last name, which is kind of good because I have a weird last name, so hopefully it should give me an advantage. And in this chapter, we're just going to use Hirish-Chandra's theorem to obtain formulas about characters and multiplicities of finite dimensional L modules. So our first topic here is we're going to look at some functions on H star. So for a lambda in lambda plus, recall the formal character ch lambda of v lambda, as ch lambda being the sum over lambda over mu in our set of weights, as m lambda mu e mu, where the e of lambda, e of mu form a basis for the group ring Z of lambda. So you can also define formal characters for infinite dimensional modules, Z round brackets of an individual lambda. But it says here that it's awkward to kind of work with the infinite formal sums, so instead we're going for what they call a more suggestive formalism. So this Z square bracket capital lambda, this can be viewed as the set of integer valued functions on our set of weights, which are zero outside a finite set, don't know why I wrote the word unite, side a finite set in which our product is the convolution, which I know I've worked with before when doing this kind of math in a formal context, although it's in a bit more analytic of a setting than I would normally care for personally. But we have that convolution. Remember, Vg over lambda, in this case it's going to be over the sum of mu and nu being lambda of f mu, g being nu, because this is the discrete version. Now we're going to let this fancy x be the space of all f valued functions f on h star whose support, which we call as just the set of, it's basically the inverse image of everything except for 0. It's the complement, I believe, of the kernel. It's going to be any lambda in our h star which doesn't evaluate to 0 on f. And his support is included in a finite union of sets of the form lambda minus a sum for alpha being positive of k alpha of alpha, for k alpha being a positive integer. So such a set, I don't know if they're referring to the support or x, or fancy x, being the set of weights occurring in a module z lambda for lambda in h star. And we see that our fancy x is closed under convolution becoming a commutative associative F algebra containing the formal character of any standard cyclic L module. Now, we may think at times of an f in our space of x of these f valued functions on each star as a formal combination of lambdas in our h star, with coefficients, of course, in our f. So and the I'm going to need a new paragraph for that, new line for this. Now, corresponding to our earlier E lambda is the characteristic function eta lambda of lambda being 1 and eta lambda for mu being 0 for mu being non-lambda. And from this we get that eta 0 is the identity element of the ring of our fancy x, and that the convolution of eta of lambda and eta of mu is the eta of their sums, the character of their sums. And we see that the Weyl group acts on Z lambda. I don't know if this Z was supposed to be the integers. It's weird just how they notated it. But it acts by, we recall that sigma inverse of f. We saw this with sigma and sigma inverse flipped, I think, but it's going to be sigma of lambda. With sigma of eta lambda being just eta of sigma lambda. So we're going to do a little more setup in our fancy X for next video probably. So let p lambda be the number of sets of non-negative integers k alpha for positive, alpha positive, for which minus lambda is the sum of alpha being positive for k alpha of alpha. Of course, p of lambda is 0 unless lambda lies in the root lattice. And we want to notice that p is equal to the character of said round brackets of 0. With p then being an element of X called the constant. I don't like how to say this name, maybe I won't, I don't know, function. And it says it differs from constant's partition function only by change in the sign of lambda. Next, we're going to let Q be the product for positive roots of eta of alpha over 2 minus eta of minus alpha over 2. With our product in this context, of course, being the X product, which we saw is convolution. We're going to call Q the vile function. And then we're just going to go through a bunch of smaller lemmas for these various functions. So, one last bit of setup for a function. We're going to let f alpha of negative k alpha be 1, and f alpha of lambda otherwise be 0. For each positive root alpha, and k being a positive integer. And we know that symbolically f alpha is e0 plus eta of negative alpha plus eta of negative 2 alpha and so on, kind of. Thus f alpha is in our fancy x. And we have 7 just really small lemmas with really small proofs. First one, part A, P is the product for positive roots of our f alpha. Part B states that eta 0 minus eta negative alpha convoluted with f alpha is eta of 0. And part 3 states that Q is the convolution of eta of our delta with the convolution of our positive roots, eta 0 minus eta minus alpha. The proof. Alpha is by convolution, is by definition of convolution. B is just that eta 0 minus eta negative alpha convoluted with eta 0 plus eta negative alpha plus eta negative 2 alpha and so on is just eta 0 by cancellation. This isn't really rigorous, but it's not hard to work out the details. And recall that our delta is the half sum of our positive roots. We get that by bringing this half in, which I should have done. We get that eta of delta is the convolution of eta of our alpha over 2's. But we have that eta 0 minus eta of minus alpha convoluted with eta of alpha over 2 is eta alpha over 2 minus eta of minus alpha over 2, giving our result. Alright, our second lemma, lemma B here we could call it. Sigma of Q, that's not a Q, that's a P, is minus 1 to the length of our sigma times Q, for of course sigma in the vial group. Now, as always, vial group is generated by simple reflections, so we can let sigma be a sigma alpha. Let sigma be the reflection generated by an alpha. As sigma alpha is negative alpha and sigma permutes the other positive roots. Sigma alpha of Q is negative Q. And then you just repeat this to get our negative 1 to the L sigma. Our third lemma, Q convoluted by P convoluted with E negative delta is just a epsilon of 0. And this mainly comes from our first lemma. We get that Q composed P convoluted with E negative delta is a convolution over positive roots of epsilon 0 minus epsilon negative alpha convoluted with epsilon of negative delta, convoluted with p, convoluted with epsilon of negative delta. I think I said that for the first time, but that one's supposed to be positive. This is just a convolution over positive roots, of course, of E0 minus epsilon negative alpha, convoluted with our p, which is itself the product over positive roots of epsilon 0 minus epsilon of negative alpha, convoluted with f alpha, which is just, we saw, our epsilon 0. Alright. So, 1 second, we'll move on to our fourth lemma. This one I don't even bother really giving a proof, so I won't really bother giving a proof. It's the character of z lambda of mu is obviously going to be p of mu minus lambda, which is a convolution of p on epsilon of lambda on our mu. And another immediate lemma is that the convolution of q on the character of our z lambda is epsilon lambda plus delta. This is from our previous two lemmas now. And one last thing to note before we end off here. The coefficient of -1 to the L of our sigma will be set equal, will define our Sn of sigma. Recall, if our L is of type A of L, the file group is isomorphic to the symmetric group of L plus 1, and Sn of sigma is just the sign of the permutation of sigma. And I think we will be calling it here. Yep, that's about right length for video. Next time we're going to look at some of these actual formulas. Like the next 3 chapters are the 3 formulas we kind of like gave in the title. This is all just like setup work, and so I'm going to leave a video in between and take a break in between this and the next video so you have a nice chance to forget about what you learned here. And thanks for watching.